In this video, I'm going to be re-recording the 2022 HSC trial exam that I wrote for my class. So, first of all, it's actually 99 marks, so I think I made an error somewhere, so a little bonus for those people who did the exam. Question 21. First of all, it's a reduce, reuse, recycle. If ever you see the opportunity to design away a problem, the answer is always fix the problem in design. This is true for corrosion questions. This is pretty common. So if you see the option to reduce in the design stage, that's what we should be doing, always. Right? We want to fix our problems in the design stage. Okay, question 2. Which best describes gears? Now, gears need to be wear resistant because those teeth are in constant contact and there's a lot of abrasion. So they need to be hard on the outside surface. They also need to be tough when you drive over a pothole. So we need induction hardening provides a hard exterior is the answer we're looking for. We can use induction hardening or flame hardening. We don't talk about that in a whole lot of detail. They're both processes where we get hardness on the outside and softness on the inside. The thing to note is that they we can also use flame hardening. Why do we like induction hardening over flame hardening? Because induction hardening, where we use electricity instead of a fire, is electricity is a lot easier to automate, much more easier to automate. So that's the answer there. Annealing, it's true that annealing does produce large grains, but not large brittle grains. So that helps us to get that, to know that answer is wrong. But also, we don't really anneal gears, right? The example we always like to use for annealing is pineapple tins. Things that can be soft, so that if you drop your pineapple tin on the ground, it dints, it doesn't break, right? It needs to be tough. Okay, question 3. This is forged, right? We can see that it's clearly been forged. Why? Because we can see the grain flow, right? We can see that the grains of this object flow around the object. Past HSC question, very happy with this question. There's no problem with that. For casting, we will have grains that form around the outside. The sand casting and die casting will give different effects because we know that the metal will cause more commular grains because the heat is going to be drawn out faster. That's a little bit like, that's a higher level question asking you to compare different kinds of casting. And you might have inclusions, like little errors, like little voids when casting. Extrusion, again, I'm not going to look up extrusion for flow, but we're going to get something that follows the shape a little bit more than if we say machine. So if we machine, we're just going to have all of our grains go north-south or east-west or whatever, and we're going to remove it. The advantage of forging is it doesn't have the points of weakness that machining would have. Okay, question 4 is toughness. Toughness is the area under the curve. That means if you've got a crayon out and you're going to color in the shape, you drew that line down and you colored in that shape, A is going to use the most crayon. Toughness is the ability to withstand impact, so if you drop it is an example of where we want toughness. Okay, so in this question here, I haven't asked you to compare. So I was looking at some independent papers recently, and I just really like that the independent papers in their solutions, they just say that VR equals big area divided by small area. I really like that working out. If we're talking about diameters, if they don't give us areas but instead give us diameters, what we can say is big diameter divided by small diameter squared, because the ratio of diameter to area is squared. So just be really careful. In this case, I try to only bite to test you on things once. And because I'm going to test you on calculating areas later, I didn't want to have you calculate areas this time. In a different paper, so if you're watching this in the future, if you're the class of 23 or beyond, then you might not, this question might not be relevant to you. You need to pay attention to see if it's diameter or area. And I gave you, in this case, area. Okay, so in this case, the area ratio is 5. The velocity ratio is 5. So that means that if we're applying 10 newtons into X, we're going to get 50 newtons out. Okay, just quickly I'll mention that because we never get anything for nothing, because the work needs to be the same, if we're getting an increase in force, how do we get an increase with force doing the same amount of work? We can't get free energy. So what's the formula for work? FS, that's exactly right, the sweaty man. Yeah. Okay, so that means that if we've got a smaller force, it's going to have to go a bigger distance. Yeah, a smaller force, a bigger distance. I was looking at some, like I said, some independent papers, and they might include mechanical advantage into that equation and with efficiency. So that's something you can be aware of. We said the velocity ratio is equal to big area over little area, but if there's inefficiencies, then that's going to reduce the amount of distance traveled. The distance traveled is velocity ratio. The force is determined in actual real world is determined by mechanical advantage, and mechanical advantage is the efficiency times the velocity ratio. Okay, I think we've said enough. We can move on. Question 6. Which form of radio is most susceptible to static interference? Amplitude. AM radio is the one that is most likely to be affected by just spikes from the engine or lightning or those sorts of things. They will interfere with the radio signal and distort the radio signal. They will increase the energy, and when they increase the energy, that's going to increase the amplitude of the wave. And when you increase the amplitude of the wave, that is going to distort AM radio. It won't demodulate properly. Okay, we've got different kinds of glass. Borosilicate glass, soda lime, laminated, and toughened. Now, I had some students say, well, sir, isn't toughened, it's in the name, right? Toughened is the ability to withstand impact. Yes, it's true that toughened glass is better than regular glass. But remember we watched that video of the guy with a baseball bat breaking the different windows, and he was still able, when he hit the toughened glass, yes, it did withstand some impact. Yes, it did. It withstood impact more than plate glass would. But the laminated glass, which is a composite material of 2 layers, it's like a sandwich where instead of having bread, you've got glass, and instead of having jam, you've got polyvinyl butyl, PVB, and or peanut butter would have been a better analogy. Anyway, that acts as a glue that holds those 2 layers together, and even when you hit a moose, the windshield can still hold together sometimes. I mean, mooses are ginormous. Is mooses? I don't know. Anyway, 8. Which of the following is not a benefit of optical fiber cable compared to copper? Now, I probably would have been better off reversing this question. I probably would have been better off saying which of the following is a benefit and then negating all the other questions. But here's the thing. Optical fiber does have improved bandwidth. Tick. Right? So that's good. Optical fiber does have greater data security. Tick. Optical fiber does need less repeaters. So if you're running copper wire, you need to have repeater stations to deal with attenuation. That's signal loss. Right? Optical fiber can go a lot further without having signal loss. Now, optical fiber does not conduct electricity. So therefore, it does not have improved conductivity. Do we all see that the answer is C? Yep. Okay. I've got a combination of logic gates here, and we're going to use these to calculate the output. So we're just going to say, what would I do in this situation? They've said that everything equals 0. 0, okay, A, B, and C are 0. Oh, I like that. I don't have to go through. Okay, so if A and B are 0, this is an AND gate. So that means D is going to be 0. If B and C are both 0, this is an OR gate. That means these are both going to be 0. And then if I have 2 zeros going into a NAND gate, sorry, this is a NOR gate, right? So a NOR gate is going to say, are either of you on? And so let's just do the OR component first. An OR gate will say, look, you have 2 people, Kate and Lily, they both want to get into the club. Neither of their names are on the list. The bouncer is going to say no. And then you have crazy Missy Elliott, the manager, and she comes along and she flips it and reverses it. And yeah, right? And it turns it from a 0 into a 1. The not dot, right? The not dot flips it to a 1. Now, I will tell you that when I was at uni, I had a moment where I was, oh, it's the circle that makes it a not. I didn't understand. Sometimes I thought it was longer or shorter. For you, just remember the not dot. Just do it without the dot and then add the dot in and flip it and reverse it. The crazy manager who just says, yeah, I know they're not on the list. You're going to let them in anyway, right? And then people who are on the list, she kicks out. She's crazy. She's crazy, that Missy Elliott. Anyway, song from 20 years ago. Okay, so we're going to have 0, 0, 1. Is that an option? C. Okay. We are going to go from AC to DC, rectifying a circuit. So, first of all, we've got a diode. A single diode is going to give us half-wave rectification, A. Some of you guys are going to say but I went A. I went A. Why didn't I get the answer right? Because there's a capacitor. right? Here, does anyone know what kind of capacitor is? It's a special kind of capacitor. Electrolytic is exactly right. 10 points to Gryffindor. It is electrolytic. It's a polarized capacitor. Anyway, I don't think that really matters too much, right? A capacitor will smooth. I mean, obviously it does. They wouldn't use it in that diagram, but even if it didn't have electrolytic capacitor, capacitors smooth out the wave. This is really important. This is how we demodulate AM radio. Yeah, we're going to go into that in more detail after the trial. And if you're listening to 2023, I might even include it before the trial. So watch out. But for my kids in 2022, we're going to talk about that in a week. This here. So A is the unrectified AC wave, right? And C is a full wave rectification. If anyone's an Electro Boom fan, this is like his shtick. This is like his sort of catchphrase. He's a big fan of full bridge rectifiers. He's got like a 3-minute supercut of just him saying full bridge rectifier over and over again. You can buy a T-shirt that says full bridge rectifier. Okay, not some puny. Yep. Yep. D is correct.
Is that where the capacitors being applied to A or C?
A. So it would be A, then D. A, then D. If they would need 4 diodes for it to be full wave rectification. But yes, a full wave rectification can be smooth. So that's a great question, and definitely glad that you asked that. This video will be better because you asked that question. Okay. So this question here, I don't know, this was in a paper somewhere. It actually had nice pretty arrows, and it doesn't look as good when I draw it. But this question is precipitation hardening. Now, precipitation hardening is something that wasn't really in the paper 5 years ago, 10 years ago, whereas now it's showing up with increasing frequency. You should have some concept of precipitation hardening. Our class in 2022 has gone into a lot of detail. We watched Mr. Fairbank's videos on engineering studies and cabinet maker video. We watched the real engineering video where we talked about precipitation hardening. So there's quite a lot going on there. But for us, it's just the idea that we need to, after we quench, instead of tempering where we heat up for a short time, we're going to age harden, which is going to increase its temperature for a long time. And there's an optimum aging. You can over-age and you can under-age. Okay. For satellite communication, what we're looking for is the satellite communication, the same as Wi-Fi and Bluetooth. They all operate in the microwave range. Microwaves are in gigahertz. Now, you might be familiar with your router, right? My router at home, I have Duck and Chicken. I've said on other videos, right? Duck and Chicken is the fast one. That's the 5 gigahertz band. And I also have Batcave, which is, no, it's the other way around. Anyway, I've got these two stupid names, but anyway, one of them, Batcave is the fast one, is 5 gigahertz. Whereas Duck and Chicken goes a long way. And that way, my daughter, she has to use Duck and Chicken because her room is further away from the router. Yeah? Okay. So we've got a question here. Question 13. The answer being D, just in case I wasn't clear, right? We're talking about gigahertz range. Okay, question 13. What we've got here is we're calculating parallel resistance. Now, I just want to check that I have some pictures. And I just want to check that I don't think I did a calculation for this, right? It's a bit odd sometimes when I'm recording, I've got to try and be really careful to move things around in the right way to find my files. I did. Look at me, past Luke. It's not as pretty as when I do it on the whiteboard. I do really apologize for that. And, I wish I kind of did it on the whiteboard, but I didn't. Let's see if I can zoom out. That's what I need to do. Okay, the formula sheet, which I'm too lazy to show now, you'll just have to trust that there is a formula sheet. That shouldn't be news to anyone doing a trial video that formula sheets are on the paper. Say that the total resistance of a circuit in parallel is equal to the inverse of 1 over each resistor. So in this case, we have 2 resistors. We have, 1 over 2 plus 1 plus 1 over 3. Let's just quickly go back to our paper, and we can see 1 over 2 plus 1 and plus 1 over 3. Now, that's the same. For those of you who are quick at maths, you'll know that that is the same as 1 over 3 plus 1 over 3, which is the same as 2 over 3. Now, because we have to invert that, it gives us 3 over 2, which gives us an ohms of 1.5 ohms. Now, there are some questions where they talk about ohms hours, and I haven't talked about that yet. That's one of the things that I need to talk about for the class of 2022. That's something we need to talk about after this paper. It's one of the 4 or 5 things that we're going to talk about, is calculating batteries in ohm hours. It's not that hard. You just find out how many, sorry, I said ohms hours. I meant to say amp hours. You just count how many amps and how many hours, right? It's really actually not that difficult. But once we've got the resistance, we can then say V equals IR. So we're actually going to get the true Ohm's law, which is I over VR. We use the little triangle here. If you don't know what this triangle is, come and ask me, or ask one of your fellow students. And so the volts is 18. Volts divided by 1.5 gives us 12 amps is the answer. And we're back to the paper. 12 amps is C. Okay, which flight control surface on an aircraft controls pitch? When I recorded this video last time, I recorded the video before the paper went out, and it was good because it helped me spot some weird spelling errors, and this sentence didn't make sense. If you watch that video, you can see that the text is wrong. You can't hear what I was saying, but because I didn't turn the microphone on. But yeah, so which controls pitch? The elevator, right? We think of Fat Amy in the elevator, and she's singing in the elevator because she's pitch perfect. Yeah, that's what we're going with, right? The elevator controls pitch. Okay, so which of the following is used in aircraft to address the risk of wing stall in fixed wing aircrafts? That is slots, right? There's a slight difference between slots and slats. Slots don't move. Slats, like Michael Slater, who I learned has since been cancelled. I don't really pay a lot of attention to cricket commentary outside of the Ashes, and I was surprised to hear that Michael Slater has been kicked off the Channel 9 commentary. But yeah, so my picture does say I don't endorse Michael Slater or slot machines. Okay, so 16. This is a phony friction formula question. So first of all, well, I have written out some notes. Again, they don't look as pretty as they could, but, we're just going to have to deal with it. Okay, so here we've got phony friction. So we're replacing the F with a PH. You get it? Okay, and we're replacing N with mg, weight, plus or minus the vertical component of P. Now, in this case, we've said, are we making the thing heavier or lighter? Well, we'll have to go back to our picture really quickly. We're making the box heavier, so we're going to increase the weight of the box. That makes sense? We're increasing the weight of the box, so we're going to be adding. Yeah, not subtracting, we're going to be adding. Okay, now, in this case, pH is P cos, and PV is P sine. Now, because it's 30 degrees, I'm going to pause. So, resuming the recording, and we were talking about how if P is at 30 degrees, we can reasonably assume, we can reasonably know that for a 30-degree triangle, the short side is half the side of the hypotenuse. So the vertical component is going to be half of P, or 0.5P, and the horizontal component is going to be the disco number, 0.866. And that was something that a student I was working with, they're like, oh, I got the disco number and the pundit number mixed up. So 0.866. So this is how we get the 0.866. So P cos 30 is the same as 0.866P. Mu is 0.4. Our mg is 19 times 10 for gravity, 190, plus 0.5P, because we know that the vertical component is equal to half of the hypotenuse, or 0.5P. So what we can do then is the first thing is really important to expand the brackets. I'm a big believer in drawing the two arcs. I didn't do it here, but drawing the two arcs makes you less likely to make an error with expanding your bracket. And so what we've done is 0.5 times 190 is 76, and 0.4 times 0.5, well, half of 0.4 is going to be 0.2. Now, do you notice I make a big point of writing plus 0.2, because I know that I make a mistake. I know I make that mistake often. And then what I have to remember is that when I move it to both sides, this is a thing when I was in high school, I never understood why teachers do this, but I'm going to minus 0.2p from both sides. I was talking to a maths teacher the other day, and I was saying the same. He said the same thing. It's funny that maths teachers generally don't do the minus 0.2, but when you teach it, you kind of have to, because otherwise it's not clear what step has happened. Okay, so then we get is, so if we had 0.86, so 0.866, the disco number, minus 0.2, well, now we've got 0.666. So what's that? 1/1000th of the number of the beast. Anyway, 76 divided by 0.66, or 76 divided by 2/3, is going to equal 115. So we're going to get our answer of 115. Okay, so 17. This question I just took entirely from a past HSC question. I was going to say that, so the image shows one end of an electrical spark plug used in an internal combustion engine. The component M is made of alumina and engineering ceramic. Which of the following best justifies the use of ceramics in spark plugs? I think I maybe changed a little bit to make it, I think I clarified it. But anyway, what are our choices? We've got impact resistance. Well, ceramics aren't really known for impact resistance. Low conductivity, bingo. Low costs, maybe, but not lower than not lower than plastic, right? Plastic would have been cheaper, right? What about machinability? Well, ceramics, they're not super machinable. So the answer we're looking for in that particular case, we're talking, even the fact that we talked about internal combustion engine, we should reasonably understand that internal combustion engines are hot. So what we're looking for is low conductivity. And so it's both low conductivity of heat and electricity. I just think that in terms of low cost, well, it's not cheaper than plastic, and it's certainly not as machinable as plastic. The reason we're using it is because if we use plastic, it would melt. So, question 18. What are two advantages of using powder forming to manufacture a self-lubricating bearing? So, I think I took this from a past HSC question. Well, let's have a look. Because it's self-lubricating, we're probably going to look at something to do with porosity or density. So high density is the opposite of high porosity. So porosity is how many holes. Think of the pores in your skin are little holes, right? So we want high porosity and low material waste. I think that's the answer we're going with, is 18B. By all means, if I have marked something else different on the paper, right, I'm going through this fairly quickly. And even though I've just looked at 25 papers and I've already recorded this video once before, please let me know. Okay, question 19. It says a diagram is loaded showing the corresponding shear force diagram is shown. Okay, calculate the maximum bending moment of the beam. The original question said where was the maximum bending moment going to be? Now the obvious locations are either at A or at C. Why do we know that the maximum values are going to be at A or C? Based on our calculus, what can we tell? Where we cross the x-axis, what happens? We get our maximum and minimum values, right? Using calculus. So we know our maximum and minimum values are going to be at A or C. So which one is it going to be? Well, remember, when we want to calculate the bending moment, there are a couple of ways we can approach this. One way that we can approach it is that we can just look at the area of the box. So here we have 4 times 2 is 8. That's the area of this box, 8 kilonewtons. On the other side, if we're looking at C, if we're going from this end, it's 5 times 2, that's 10. So that's the answer we're looking for, is 10 kilonewton meters. Now, because of the nature of this beam is going to have a cantilever, right? When we look at beams, what we want to look at is we want to imagine that this beam is going to, I think I actually have drawn pictures here. Let's go and have a look. We do have a picture. Okay, so the first thing I've done is I've said, well, this beam, how is it going to deflect? It's going to deflect something like this, right? It's going to deflect something like this. Now, that because that's how it's going to deflect, we reverse that image and we're going to say, well, okay, we're going to have, because it's point loads, it's going to be straight lines, so it's not going to be curved. If it was UDLs, it would be curved. And we said 8 and 10 were our two values. And that way it matches up. Now, you notice I've written a dash next to the 8. That was just me, slip on my pen. But this one here is minus 10 kilonewton meters. What that means is just that the reinforcement needs to go on the top of the beam, not on the bottom. That's all that means. But when we're talking about a steel beam, we don't care if it's top or bottom. A steel beam, all we care about is the bending moment. And so in that case, if we're using, say, an I-beam, we're just saying, yep, divide for 10 kilonewton meters. That designed for 10 kilonewton meters. That's our answer. Okay, so we're going to move on. Okay. Here we have a bracket and an assembly pin shown. Now, I have got this answer already for us. We've found this answer. I wonder if I can remove that pane. Doesn't look like it. We're just going to accept it. Okay, so the difference between our question and the question here is that they had a factor of safety of 5, and I just took the stress at 24. I just started off at that value so that way we'd get the same answer. So I said, or I think I increased the load, whatever it was, because I think there's 2 methods we can use. 240 is the allowable shear, and the load is 480. I said the load, I just divided the load by 5. That's how I got the same answer. So that way, because this question was worth 3, when it's a multiple choice, a 2-mark question when it's a multiple choice could easily be worth 1, because you can look at the various answers, and that helps you. That gives you an idea of what sort of numbers. You can also, with a multiple choice, another thing to remember is if you have no idea what to do, you can always start with A and work up. And then if that didn't work, start with B and work up. I remember when I was doing tutoring for selective school tests, and there was stuff that I would see in these Year 6 tests. I'm like, there's no way the Year 6 student should know this. And then I realized, no, they give you the options, and what you can do is if you start with the options, A, B, and C, that's how you have to solve these questions. You have to plug in those numbers. Okay, so what are we going to do? We're going to go back to that question. We'll have a quick look at what they've said. So what they've said is, once we've got this force over stress, we know stress equals force over area, so we can rewrite the equation. They've written P instead of force, right? But we've rewritten the equation as area equals force divided by shear. So they've identified it as double shear. And I'll just quickly comment on that if we go back to our thing. So let's assume that we're pulling on this middle part. Effectively, what this bracket is doing is it's pulling towards the wall, towards the wall, towards the wall, away from the wall, away, 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 towards, towards, towards. How many changes of direction were there? So back, 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 front, 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 back, back, back. How many changes? 2. So it's in double shear. If in doubt, it's double shear, right? If in doubt, if you don't know what it is, if you see shear and it's a bolt, just assume that really, really look, and if you can't figure it out, it's probably going to be double shear, right? I've been taught that by other HSC markers, and they've just said, look, sometimes it's not, right? Sometimes it's not. But if you have no idea, you're better off assuming double shear than not doing anything with the area. Okay, so I won't go through this in too much more detail, but I will point out that so once we get this area of 36 millimeters, we're then going to use pi d squared on 4. Now that's something you should be familiar with. You should be familiar with area is pi d squared on 4, and that diameter can be calculated as the square root of 4a on pi. Now, even if you just are working that up from some other system, it's just much easier. This is why I always tell people you're much better off using, as engineers, pi d squared on 4. And I remember when I was in high school, I didn't listen. I didn't listen to my teachers when they said that. But when I started working professionally as an engineer, I always used pi d squared on 4. Why? Because they never give you a radius, right? Now, I understand why maths teachers teach 2 pi r. I understand, or pi r squared. I understand why they do that. But I'm just saying, if you can make the switch, and especially if you're planning on working in engineering, make the switch now. Okay, what we get is an answer. We get an answer that's 6.8. You can't buy a 6.8 bolt. So of the options available, it has to be 7 millimeters. Does that make sense? Okay, great. Moving on. Okay, so we're now on to our extended response, and what are we going to look at here? Okay, so the first question here is a Young's modulus question, and we know that when we see Young's modulus, we should be thinking E equals flea. An always important thing to remember is that E in E equals flea, the vowels can be swapped, right? You can spell flea as flee, like run away, or you can have it all be capitals. Little e equals big, little e equals big F over times big L divided by brackets big E times big A, right? But in this case, we're not using E equals flea. Instead, we're going back to the formula sheet, and we're going to say that Young's modulus equals stress over strain. Now, they've given us the stress. The stress is given as 150 megapascals. As for strain, what's the formula for strain? Extension over length. And so the extension is given as 0.103 millimeters, and we want to use the original length, right? The original length of 80 millimeters. Yep. Okay, and I tried to make sure that all the numbers were different so that way it was clear. This question, I modified a HSC question where it was asking you to calculate the strain based on the change in diameter. I didn't want that question, so I instead rearranged it. Okay, so we're going to do question 21. It's a truss. And the first thing we're going to do is we're going to find the reaction at K. We need that reaction in order to solve the next question, right, to find our members. Let's say that you somehow don't know how to do, you have an instantaneous mind blank and you don't know how to find the reactions. What do? You just say K equals 100 so that way you can answer the following questions, right? Just insert a value and people will pay the carried error. I definitely did. When I marked this paper, I paid people who wrote the wrong value for K, but they used that value. They continue to use that value in the question below. Now, what we're going to do is we're going to find, after that, we're going to find GI, which is this top beam. We're going to find HI, which is the diagonal. And then we're going to find IJ, which is this one here in the corner. Okay, so let's have a look at some drawings that I have done. So I did that formula, even though we already had the answer there. But okay, so you can have a look at that later, if you're really keen. We don't... Sorry. I might have to adjust that camera in a second. Okay, here's the one we want. And what we're going to say is... Oh, okay, yeah, here's the working out. I didn't realize I did the working out for this one. Okay, so I've just written a data sheet. I've said like the original length is 80, the stress is 150 megapascals. The change in length, also written as E, delta L or E, is 0.103 millimeters. The area is, the original area is 100 millimeters squared. We could use E equals Fl, except we can't because we don't know the force. Instead, we're going to use stress over strain, and we're going to write stress over, and we're going to sub in the formula for strain. We just type those numbers in and we get the value. Just remember, we go together like megapascals and millimeters squared. We've used millimeters and megapascals, which means our answer is going to be in megapascals. So we're going to get 116 times 10 to the 3, which equals 116 gigapascals. Okay, for the reaction, you just saw that because it's symmetrical, I can find the reaction by just taking those values and dividing by 2. Now, there are plenty of people who solved it the correct way, and there's nothing wrong with that. You're not going to no one lost marks because they solved it correctly. What I'm saying is, have a quick look, and if it's symmetrical, think, you know what? I'm going to use this as a check, right? Do the correct way anyway, by all means. But just check and say it's symmetrical. Even if it's not symmetrical, think, what would the value be if it was symmetrical? Okay, so now I'm going to move on. Well, first of all, what we're going to do is we're going to find GI. So we've said that GI is this vertical beam. And when we look at GI is our target, and GH and FH are our distractors. Well, they share a letter, so we know that they meet up. They meet up at H. We're going to take some of the moments about H equal 0. So we're going to have 120, which is this downward force, multiplied by 0 because it passes through H. We're going to have FH and GH both multiplied by 0. We're going to have GI times 3. Why is it 3? Because they've given us the perpendicular distance of 3. And we're going to do 196, the reaction, times 6. And again, they've told us that value. If we then do some basic algebra, we can see that our value is negative, right? We assumed tension. We assumed it was pulling out, and if it was pulling out, it was going to be anti-clockwise. And if it's anti-clockwise, therefore it's going to be, we wrote that down as negative. GI times 3, we had a minus sign there. Because we could see our answer was going to be negative, we said our assumption was no good, therefore compression. GI equals 190 in compression newtons. Okay. So that's how we're going to solve that. Normally we write the compression after the N. I got excited. Okay, so now we're going to find HI. Now in the case of HI, we can see GI, HI, and FH. Only HI has a vertical component, right? We can see the GI and FH, they don't meet up anywhere. They're parallel. They're going to go forever and never meet. But HI, it has a vertical component. So we're going to use the lone wolf. HI is the only one who can take that 190 force. Right, so that 190 force has to be cancelled. We have 190 up, so we're going to need 190 down. Who's going to provide 190 down? HI is going to provide 190 down. Now, HI is a diagonal, so that the hypotenuse is going to be bigger than 195. It has to be a number bigger than 195. The vertical component is 195, but HI is going to be bigger than that. So what we write is HIV, which is an unfortunate acronym, but the vertical component of HI is 195. Therefore, HI equals 195 divided by sine 45. Now, for me, I just know that it's going to be divided by 0.707. I know sine 45. I know that's a number less than 1. I know I need a number bigger than 1. So what I'm going to do is I'm going to divide. So I get 195 divided by 0.707, which is sine 45, and that gives me 276 newtons. And because we can see that pulling out is down, and it needs to be going down, pulling out is tension, so it's in tension. IJ is a zero force member. How do we know that it's a zero force member? Because it's on the corner. There's only 2 members at a joint with no external forces. The alternative way that we can find a zero force member is if we have 3 members that all meet, where one of them is where they make up a 180-degree angle. Again, a zero force member can never have an external force. Now, I would suggest that being able to recognize zero force members can definitely improve your life, right? At least for the HSC. Okay, so I've already given the answers there. We're going to move on. Okay, we've got a 6-meter beam shown. We're just going to go straight to our calcs, and we'll go from there. Okay, so what we've said is, first of all, we need to find the maximum bending moment. So I've drawn a little diagram here. I've said that the reactions are 6 and 6 because it's symmetrical. It's 12 kilonewtons down, so the reactions are going to be like this, 6 and 6. Which, because it's a 6-meter beam, each side of these rectangles is going to be 3 and 3. So the area of this rectangle is going to be plus, so 6 times 3 is 18, and it's positive 18. And then this one's below the axis, so it's minus 18. So it's going to go up to positive 18 and then back down to 0. And that gives us 18 kilonewton meters. We rewrite 18 kilonewton meters as 18 times 10 to the 6 newton millimeters, because we go together like megapascals and millimeters squared. Now you'll notice that I've written M equals PL on 4, and you're allowed to use that because it's a simple symmetrical beam. Now, I would recommend that drawing this diagram is just as fast, and you can't get that wrong, right? But if you use PL on 4 as a check, then that's great. There is also the method of actually just calculating the moments on the left-hand side or on the right-hand side, which I explained to a few students as I handed these papers back. But what I would say is that you know if you're that kind of student, I have that's in my other videos where you can go and find out more. Okay, so once we know M, next thing we need to know is we need to know Y. Now, Y is the distance from the neutral axis to the extreme fiber. This beam is going to be bending like a happy face. Now, on the top of it, because of the direction of this force, it's going to be squashed at the top and stretched at the bottom, right? And in the middle of the beam, it's not going to be squashed or stretched. It's going to be neutral, right? So we call that location the neutral axis. In a rectangular beam, we can know that the neutral axis is halfway down the beam. Sometimes they'll provide that, but there's no expectation. A rectangular, they expect you to know that if you have a rectangle, the distance from the neutral axis to the extreme fiber, which is written as Y, is going to be half the depth, in which case ours was 450 divided by 2, 225. Back to the calcs. So here we can see 18 times 10 to the 6 times 450 divided by 2, and then divided by the second moment of area which was provided. The second moment of area will always be provided, right? I have never seen an example where the second moment of area was not provided. Now, the 10 to the 6's both cross out, top and bottom, but pretty simple maths there, and we're going to get 10.65 megapascals. We can close this particular window now. Okay. Justify the use of engineered timbers in civil projects. Well, the most commonly used engineered timber in civil projects is plywood, right? It's a bit confusing because we just looked at a picture of glulam, but plywood is the most commonly used. Why do we use plywood? Formwork. Formwork is the application, right? And why do we use it? Because it has bidirectional strength. It's strong in both directions, right? Also, it's free of defects. If there's any knot holes, you just cut that piece out, right? It can also be made, engineered timbers can be made to virtually any size and shape, unlike natural old growth timber. You can't buy 20-meter lengths of oak. They just don't exist. So this is the advantage that we have by using... So could someone get, Alex, could you get for me my answers? They're the one that doesn't have the staple cut off. All the other ones have the corner cut off. Also, it doesn't have a name on it. Also, there's writing on it in red. Okay, so that's the thing that I would look at. There's other applications. If you listen to the Sand podcast, my favorite ever podcast, they talk about the use of engineered timbers as an alternative to concrete. Okay. Compare the properties of cast iron to steel. Now, there are 2 to 4 things that you need to know about cast iron. Everyone who's in the classroom, they can see me making a C with my hand, right? Cast iron, right? Cast iron starts with C, right? Like I'm doing my Cookie Monster voice. Okay, cast iron starts with C, and there's 2 to 4. So I'm doing my fingers 2 to 4 things we need to know. The first is that cast iron has a lot of carbon, right? Like the Cookie Monster, yeah, carbon. How much carbon does it have? Luke, how much carbon does it have?
2 to 4%.
Oh, I'm so pleased you got that right. 2 to 4%. Okay. Now, cast iron is only strong in one direction or in one form. What's that? Compression starts with C, right? So, cast iron, right? C is for cast iron. That's good enough for me. C is for carbon, right? 2 to 4%. C is for compression, right? Which brings us to, I don't know if I've ever shown this class, K is for compressor, right? I'm definitely not going to get finished by the end of this lesson because, oh, there we go. It was meant to be. K is for compressor is pretty cool. Cool with a K. Anyway, probably for the best I didn't show that. Okay, so what are the 2 main differences between steel and cast iron? Well, okay, cast iron is only strong in compression. Steel is much stronger in tension. Also, because it doesn't say mechanical properties, you can also talk about other properties like its carbon content. So you can say steel has a much lower carbon content than cast iron. Right? You can say cast iron is good at casting. Steel is better at rolling and being forged. Right? Now, then there's some other properties because, people can write literally anything, right? They could say, well, one of them is more magnetic. I don't know which one's more magnetic, right? But presumably they're not going to be equally as magnetic. So what are some answers we're going to go with? So you can say that cast iron is slightly cheaper. Cast iron has slightly more corrosion resistance. Cast iron is more machinable. When I say there's 2 to 4 things for cast iron, the other 2 things, right, the 3 and 4, cast iron is more machinable because of the graphite, and cast iron has vibration dampening. Okay, steel is more malleable. Steel is tougher, right? Has more tensile strength. We talked about vibration dampening. Steel is slightly lighter. All right, but really, I just want those 2 to 4 properties of cast iron. Just when we talk about, when we're doing cube, it's important to remember justify means you have to give a conclusion, right? Justify has to say, plywood is good. Plywood is suitable for use in construction, in civil construction, for its application in formwork. Right? It's reusable. It's tough. It can be dropped. Right? So you can dump it in the truck and it doesn't fall apart. Right? So we also use steel sheet. Right? But the advantage of that a cast iron is it can be easily cut. Timber can easily be cut and joined. Okay, 2 concrete tests. Okay, the 2 tests I'm looking for. One is a cone and one is a cylinder. Right? The cone is slump, which tests workability. What is workability? Workability is when we're testing how much water there is in the concrete. Right? We want to make sure that it's easy for the concreters to use, to make sure that the truck driver hasn't poured in additional water. So we're not going to go into the slump test in too much detail here. We'll just say quickly that a cone is filled with concrete. The cone is then removed, and when it's removed, we measure how much concrete falls or slumps. Imagine if you made jelly, how much the jelly settles when it's released from the thing. There's plenty of videos. I have videos on my pages where you can see slump tests. It's worth noting that it's an empirical test, right? So it means that it has to be an exact size cone. It has to be done in a very exact method because it's an empirical test. The other test is compressive test. Again, we've seen compressive tests where we take cylinders. You can use cubes, but typically we use cylinders. We compress them in a lab environment, and we use that to determine how strong the concrete is. What happens if the concrete's not strong enough? Concrete's 3 days old, you test it, and you predict how strong it needs to be. What happens if it's not strong enough? That's me doing my impression of a jackhammer, right? You have to jackhammer it out. Way easier to jackhammer out at 3 days than it is at 3 weeks. Yeah. So this is bad time bears, right? Really big problem. Why do we have these tests? Because if you're building a bridge, you want to know that the concrete's bad before you start driving trucks over it. Yeah. Okay. Now there are some other tests. There are also transverse tests. I've seen transverse tests done when I was at uni. My honours supervisor, he was working on the use of carbon fibre to deal with cracks in concrete bridges, right? Because replacing bridges is really difficult. And so after I think the Christchurch earthquakes, he was working on this technology, and they would conduct transverse tests. Generally, though, they don't use transverse tests. We could also use X-ray tests. I don't think that's done very commonly, but I did find that people on the internet who do X-rays to see, especially if you're looking for voids in concrete. So if the concrete's not vibrated properly, you can have big air pockets, and that would be bad. And you would be able to tell that using X-rays. Okay. You should know. You should be able to describe how we use X-rays. That's a thing that I have seen in other tests. Okay, explain the benefit of pre-stressed beams. Oh, I'm really putting myself in. This is a hard question, right? I deliberately put it as D because it's hard. I have set some notes in Google Classroom that I'm pretty happy with. I also improved them after I did this test because I was reading some other people's tests. I'm like, yep, let's go with it. Explain. So if we're cubing, explain is cause and effect. Right? How and why. And benefit is pretty clear, right? Benefit means good. So what is the good thing? All right. How do we get a good thing out of pre-stressed beams? Okay. So there's two different kinds of pre-stressing, post-tensioned and pre-tensioned. Now, pre-tensioned is generally pre-cast. Why? Because you need really strong equipment to pre-tension concrete. This is where you apply a very strong force to put the reinforcement, the steel reinforcement is under tension before the concrete is poured. And then post-tensioned, you pour the concrete first, and then you apply tension. You could explain more detail, but there's not a whole lot of lines. So if you just picked one of those, if you said post-tensioning is typically done on site by pouring concrete and then applying tension to the steel reinforcing. You could talk about conduits, how we use conduits as a way of being able to pour that, but you don't need to. And the benefit of this is that it allows a greater bending load. That's all I want, right? It allows for a greater bending moment. That's all I want. I'm only asking for 2 marks. I'm only giving you 3 lines. I don't need. If you want to draw a little picture, I have no problem with drawing pictures. Go to Google Classroom. Wikipedia has has a great description. I stole the pictures from Wikipedia and I put them in Google Classroom for us. Okay, corrosion is a problem that affects steel components of vehicles and transport infrastructure. Compare 2 methods of corrosion prevention. Okay, there's quite a few that we can use. Generally, though, we're talking about surfaces, protective surfaces, or we're talking about sacrificial anodes, or we're talking about ICP or ICCP. So if we're talking about protective surfaces, the obvious one is paint, or galvanizing. Now, if you want to compare paint and galvanizing, that is A-OK. Paint provides a protective layer which prevents water and oxygen from getting to the steel. Galvanizing provides a passive oxide layer which, although not perfect, provides the zinc in the galvanizing provides a passive oxide layer, and when the steel would rust, instead electrons are taken from the zinc galvanized layer. If we're going to talk about sacrificial anodes for boats, boats are constantly in the water, and so I was talking to a student. He says, "Well, you don't put them on aluminiums." Sorry, he didn't say aluminiums, on tinnies, right? But aluminium boats don't need sacrificial anodes because they have that passive oxide layer. But for many boats, what we'll do is we'll add on zinc. We can buy from like boating stores a zinc block, and you literally attach it to the hull. And when the hull wants to rust, instead of it losing electrons, the sacrificial anode, the zinc block, loses those electrons. And what happens to the sacrificial anode? Well, we just buy a new one, right? Instead, if we have a big structure, like let's say for instance, the overhead wiring, right? This is not the case, but for overhead wiring structures, you could theoretically, or bridges, you could Really, it's used mostly for pipelines, right? If you're worried that they're going to rust and they're going to lose electrons, what you can do is you can just pump in electrons using impressed current cathodic protection, ICCP. If you write ICCP or ICP, people will give you a tick. They'll give you that mark. Okay, compare them. Because we have to compare them, we have to say how they're different. So it's a so sacrificial anodes are more suitable for things like boats, whereas the cars are particularly tend to be protected by using paint, right? Okay. Injection molding is used to produce taillights. Okay, describe it and give the method. Now, I actually happen to have, I wouldn't have gone out of my way, but I actually happen to have this answer here from 2014 paper, where it says, plastic in the form of granules is fed into a hopper, which is fed into a screw, which feeds the polymer through a heated chamber and forces it through the die to the shape required. That's good. I like that. I have my own answer that I've shared many times, where I say that typically because acrylic is a thermo-softening polymer, it means that it has to be a heated tapered screw. And when sufficient melt builds up in the nozzle, it's then injected into a mold. The mold is then allowed to cool and removed. If it's a thermo-setting polymer, it's a different process. We don't use granules, right? We can actually have two hoppers. It doesn't need to be tapered. It usually is heated, but it doesn't need to be. Okay. Moving on. I don't think I need that one either. And okay, so let's go to the next question. Okay, the chassis undergoes work hardening before being normalized. Describe the process. Okay, so I've shown everyone a picture that I drew. Unfortunately, I don't have this picture here, but what I want to say, okay, so first of all, I want you to describe normalizing, right? Pretty easy, right? It's the most commonly used heat treatment method. We heat to red hot, and then we cool it in air. This produces small EQX grains with low stress. Yep. So you could also say that it is harder than austenite, or you can say that it has greater tensile strength than austenite. Now, it's really important. Last year there was a question that asked this, and I had an opportunity to talk extensively with HSC markers about it, and they did not pay stronger, right? I'll tell you, that makes me very sad. Right? Because I think stronger is a good word. I think it adds value to the English language, and I think we should pay stronger. But they want more specifics. They want tensile strength or compressive strength. So I like to think of Kanye being banned because, he's crazy, right? It's a shame for me. I had to actually change my picture for normalizing, right? It now says Kanye is banned. He's been cancelled. Okay, but work hardening has elongated grains. So on this side, I want to see elongated grains. On this side, I want to see small EQX grains. They must be labeled. I don't care if you just labeled elongated grains, small EQX grains. That's sufficient labeling. If instead you labeled perlite and ferrite, I'm happy with that. Right? I'm happy with that. I'm happy for you to assume the carbon content and just draw that. But you have to label these diagrams. There is a mark for labeling. They say labeling. If I'm just going to say it 3 times, label, 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 right? There are marks for labeling. Please label your diagrams. Okay. Now, I said heat to red hot. There are alternatives you can say. You can say heat to 100% austenite. You can say heat above the upper critical temperature. Or for normalizing, you actually heat to 900 degrees, according to Copeland's textbook, right? I don't know. I'm not a metallurgist. But any of those 4 are acceptable, right? Any of those 4 are acceptable. Okay. So EVs, what are we going to talk about? So first of all, it's important to know that electric vehicles, you have to say that electric vehicles, there's 3 marks. I paid marks for different things. I would say that it's important to note that electric vehicles have a lower environmental footprint than petrol vehicles. That for me is the easy first mark, right? They have a lower greenhouse gas emission than petrol vehicles. It's a slightly different thing, right? Because environmental impact also includes things like the lithium batteries, right? But overall, they produce fewer, they contribute less to climate change. Now, a lot of electric vehicles run on electricity that's made by burning coal. I thought we didn't like burning coal, right? Remember how everyone made fun of Scott Morrison, right? Okay, so even if the electricity is made from burning coal, it's still more efficient. Right? It's a lot better to burn coal in a power plant than it is to burn petrol in your car, right? That's the big advantage, right? We can distribute electricity much, much more efficiently than we can distribute petrol. Now, Also, many people power their cars with electricity that came from solar or wind or other renewable forms of electricity. Okay, so it's also worth mentioning, we've got 3 marks. I've already said more than enough for 3 marks, but I'll just chuck out there that electric vehicles do have more carbon footprint in their first year of production, right? When you make them, they use more greenhouse gases, right? Those lithium batteries, they have more of a negative impact. But over the life of the car, they will be much better. Okay, describe 4 key developments in voice communication. I have so many, right? First of all, we're going to talk about Bell's telephone. It allowed people to talk to each other over very long distances. The next thing we have is radio. We could say AM radio. What did AM radio do? Well, it allowed people to send emergency broadcasts. The Titanic, every person who survived on Titanic, including Rose, who didn't share the door and then threw away a priceless diamond at the end of the movie, right? Spoiler. Right, she survived because of AM radio. If it wasn't for AM radio, every person on the Titanic would have died. Right? Also, cricket as a spectator sport comes from AM radio. People listen to the cricket. Music, right? The world of music was revolutionized by radio because now people didn't have to go and see a band. They could listen to the radio. Right? FM radio was an improvement that gave greater quality. We can we have walkie-talkies and CB radio, two-way communication. So people, this was really important during definitely World War II. I think there was some radio in World War I. There must have been, right? Because it's after the Titanic. Okay, so then we have just convenience of cordless phones, mobile phones. Mobile phones allow people to make phone calls while driving, right? And allow to be contacted when they're out of the office. We can then have satellite phones, which are really important in emergencies, right? So I'm sure that Tom Hanks in Castaway, if he'd opened that box, that FedEx box that he refused to open, and he found that there was a satellite phone in it, his life would have been very different. Would have been a totally different movie. Okay, voice over IP reduces the cost of long distance phone calls. Or Zoom, right? If the pandemic had happened 5 years earlier, it would have been a very different pandemic without Zoom. Right, with people had to go into work. If people couldn't have done remote learning, it would have been a very different world. Okay, so there's my answers there. I just want any 4 of those. Heaps of options. Just give me any 4. Explain the social benefit of UAVs. Well, okay, explain. So we need to have a cause and effect, right? But you also need to choose an application. If you just say that they're safer, well, you have to give me an application in which they're safer, right? So if you said for search and rescue they're safer, okay, well I'm happy with that for 2 marks. But because it's how are they safer? Well, they're safer because pilots don't have to fly in dangerous conditions. Or we could say deliveries, right? Deliveries of things like anti-venom, right, are better because they can travel as the crow flies, or as the drone flies in this case, rather than having to drive on poor quality roads, right? They can be used in firefighting. What's the benefit? Well, so they can fight fires I'm going to use the word firemen just so I'm not saying firefighters because otherwise. Anyway, so in situations where it'd be unsafe to fight those fires, right? At heights or in locations where temperatures or under chemical conditions where it'd be unsafe to do so. Drones were used not drones as in flying drones, but autonomous robots were used in Chernobyl. And I guess actually they didn't have drones, but they had to fly helicopters over Chernobyl. I say this because I watched the movie Chernobyl in the last year. I actually watched it during lockdown. Okay, there's drone racing. There's photography and surveying. There's my favorite, seed drones, where you can spit out seeds and you can plant 1,000 times more trees than you could if you weren't using drones. Okay, so we're moving on to question 25A. And I don't know why I don't have a picture. I know I don't have a picture for this because this is from a past HSC question. Did I close that one? Let's see. Oh no. Don't worry everyone, it's going to be okay. We have the question. It is here. Okay, so mechanical advantage equals load over effort. It's really important to remember that the pedal, right, is the effort. Where the human or the engine is applied is the effort, right? So the effort in this case is 446. Load is 72, so that's pretty easy. Right, I like to give 4 digits, but in this case, 0.6 is fine. VR is the distance traveled by the effort compared to the distance traveled by the load. The distance traveled by the effort is the circumference of the pedal. So that is 168 times 2 times pi. Now you notice that they didn't include pi. Why? Because the pi's cancel out. We're using pi on top and bottom. We just cancel out. Ignore the pi. Okay, for the big wheel, they've already given us the diameter of 675, so 675 times pi is the circumference. But what they're going to do is they've halved rather than doubling. That's fine, I don't mind. But then we have the NREV. The NREV is the big wheel is going to travel around 2.5 or 2 and a bit times compared to the pedal, because every time the big wheel turns around, the pedal has only gone 17 teeth, right? And then so 17 teeth plus another 17 teeth plus a couple more teeth gets us to 49. Okay, I can see that we're getting pretty close to the end, so I think that we're going to end it on this question. Can we finish off 25? Oh, how many actual minutes do we have?
5.
Okay, we can do that. Okay, so for question B, right, it says fight the power FV. Power equals FV, right? I don't give that in the formula sheet because sometimes, many years ago, it wasn't on the formula sheet. But so we need to rearrange that formula. We're going to write force equals power divided by velocity. Now, whenever we think about velocity, if you ever see velocity, if you're ever using velocity, I want you to think of Ed Sheeran being attacked by a velociraptor. And how many pieces is he being cut up to? He's being divided, into 3.6 parts. Always divide by 3.6. If you're thinking velocity, divide by 3.6. Because they love this trick. It's just so easy. They very rarely give you the value in meters per second. Check that it's not in kilometers per hour. Divide by 3.6. Well, after that, it's just easy maths. Okay, for 25C, what we've got is, I've made my letters wrong, but you're just going to have to accept that, sorry. What have we got here? Too many guys. Okay, so too many guys, sine theta plus mu cos theta. Okay, so I tell you that you should always expand that. I really believe you should expand that because the marker, they might not recognize the too many guys formula. That's a me thing. No one else uses that. So what we're going to say is mg is 18,000 sine 20 plus mu 18,000 cos 20. Put those numbers together. Why did we add? Because friction is making us do more work. Yeah, friction is increasing the tension, right? And because friction's increasing the tension, friction doesn't like it when you move. Because we want it to move, we're adding. If we're just trying to stop it from sliding, friction's our bro. Friction's helping us out. We just minus. Okay, so the last question, and this will be where I'll end the recording today, is we have a bike. Now, in this situation, we need to know that potential energy equals kinetic energy. And so mgh equals half mv squared. The m's cancel, just like the pi's did earlier. So we're going to have gh equals half v squared. We can simplify that. Where we end up with that is we can say that v equals the root of 2gh. I just add in, so 2 times gravity, I've written 2 times gravity, times h of 13.7. How did I get 13.7? Well, I used my trigonometry, and I said if the slope is 40 meters long, and it's a 30-degree slope, the height is going to be 40 sine 20, which is 13.7, which gives us 16 meters per second. I think we've used this exact question in the past. Okay, so that will be enough for today. I'm pretty sure we'll be able to go through and finish it off in the next lesson. I'm picking up the recording, and just before I do, I wanted to quickly talk about sketches. So this is a sample sketch for showing work hardening. Now, in this case, they've chosen some amount of perlite and ferrite. For me, I said in my video that as long as you labeled one as work hardened elongated grains and the other one as small equiax grains, that was enough. If you labeled perlite or ferrite, I gave that to you. But this is a sample. Now, obviously, this is not what it really looks like. This is an example of what have we got here? Work hardened elongated grains, and here we have normalized small equiax grains. Now, I'll just quickly make a point of what's the difference between a microstructure and a macrostructure. Things like zinc, we can see those crystals with our naked eye, right? That when we look at when you cross the road at the power pole and you're looking at those steel poles, you can see those crystals are very large, right? They could be 20 millimeters. Whereas here we can see these crystals are 5 micrometers. So definitely smaller than what we could detect with a naked eye. Okay, so with that, we'll move on. And I think the next question we're up to is this one. So this was worth 6 marks. You can see the answer here. And in this situation, we can see that we're allowed to freehand, right? Even I have spoken extensively to HSE markers when marking recent drawings, relating to marking of recent drawings, and the feedback I've been given is that pretty much there's no scenario where they won't accept a freehand drawing. What I'll say is really make sure you don't have feathering, right? A ruler can definitely be beneficial. I like rulers for getting the hatching lines. Now this is worth 6 marks, and we can see that there's the marking criteria. We can see that for 6 marks, you provide a section drawing which follows Australian standards with no major errors. For 5, you can still have some errors. For 2 to 3 marks, it provides some correct projection. So it means that you showed a front view with significant components drawn to a standard, right? So that's where you were able to get, most people here were able to get 3 marks without doing any sectioning because they had drawn the drawing proportionally, that they had carried down the dimensions. It was relatively dimensionally accurate and it looked like the right shape. And I was able to say that you were able to use Australian standards for how you showed the hex nut and bolt. Okay, so for 4 marks, we need the Australian standard. So if you drew the center line, right, I might have given you 4 marks if you'd just drawn both center lines, even if you hadn't done any sectioning. For 5 marks, I would definitely want to see the appropriate hatching, so that even if you just hatched one material, I'd be able to give you that 4 marks. But to show that they're 2 separate materials, I need to show those sections going in opposite directions. This is one area, if I haven't shown you recently, I'll show you again. I think rulers are really useful for sectioning. I think that your set square is a very effective way for getting nice, neat parallel lines. Remember that if you're using 2 materials in contact, they need to go in different directions to indicate different materials. If you have 3 materials, then what you want to do is you want to change the angle and the spacings to make sure that you can differentiate between those materials. The last mark for me, well, I mean, they don't build up by marks, they don't count up bits and pieces, they do it holistically. But in order to show that there's almost no errors, you definitely have to have some thread. And you can see a little bit of the thread here. They've decided in this drawing how much thread they've shown. You could have a thing fully threaded and you wouldn't lose any marks. They've just made a guess as to where the threading has finished. So that's that drawing for 6 marks. Okay, we'll go back to the paper. Sorry, I closed this because I thought it was done. Okay, we're at the drawing. Okay, so the 4 stages of combustion in piston engines is, now I don't give any marks. In year 10, I'll give a mark for suck, squeeze, bang, blow. In year 12, I expect people to write something along the lines of intake, compression, combustion, exhaust. Now, I said combustion. You could also say power, right? If you're a fan of that, the song by Snap or by Kanye. Or you could say ignition if you're a fan of R. Kelly. Or you could say, so I already said combustion, power, ignition. There's probably 1 or 2 others that I'm not thinking of. There's several terms that we use for that 3rd stroke. And then finally, we have exhaust. That's what I'm looking for there. I think I even paid some things that were synonyms to those words without, it doesn't have to be necessarily those terms. Okay, so then we have justify the use of high bypass turbofans compared to turboprops. I've said in the past many times that I've been on 2 turboprops in my life. One was when I was flying to a mine in the middle of Western Australian desert, and they really didn't care if that plane was 10% slower than another large passenger plane, because they're dealing with people who they're not in the same sort of hurry that commercial flights are. They also don't want to spend as much on maintenance. So the other time I went was I was flying between Estonia and Latvia, and at the time the economic disparity compared to, say, the west of Western Europe maybe is a factor of why they use turboprops. Also, in both of those situations, they were probably less concerned about the noise pollution of their airport. Right, obviously, desert in the middle of nowhere, noise pollution is not much of a problem. Turbofans require much more specialized maintenance, which requires you to pay higher wages to more specialized mechanics. But you can talk about specific features. You can say high bypass turbofans they're more efficient because they can carry a greater takeoff weight. They can have higher altitudes, and they can achieve higher speeds. But if you're traveling at low, I've lost the projector for some reason. Oh. Okay, I was about to get really upset then. Okay, so hopefully we're still recording. We are. Okay, I think that's enough. Yep, we can move on. Just if you, I'm not going to go to it now, but I have a graph that shows the efficiency. So turboprop, I think, can actually be more efficient at lower speeds. Okay, so the next thing we're going to look at is hydrofoils. And when we're talking about hydrofoils, the fundamental things I'm looking for, well, we can look at the HSE answer. Let's start there, and then I'll talk about what alternative answers I would be happy to accept. Okay, so it says at low speeds, it sits submerged. As the speed increases, the hydrofoil creates lift. At a certain speed, the hydrofoil lifts the hull out of the water, reducing drag. You could also talk about less power is needed for motors, or something along those lines. I'm summarizing because this is not the first time I've read that out loud. Okay, what did I say? I said that there is an area of lower pressure above the hydrofoil than below. I think I misspoke then. Lower pressure above the hydrofoil than below. This generates lift. That's what I'm looking for 2 marks. Low pressure above, high pressure below, this generates lift. Most people got those 2 marks. For the 3rd mark, I was looking for one of 2 things. You could either say that the lift reduces the drag and makes if you just said reduces drag, that was sufficient. You could continue as the sample answer had said about by reducing drag, it reduces the amount of power needed, it reduces carbon dioxide emissions. That would all be additional and beyond what was required. Then the alternative, very few people wrote about drag. And I can understand that. It's not something we've talked about before. And if it's not apparent that you're looking at this picture and you can see that the thing is actually out of the water, you might think, well, why would you want to generate lift on a boat? Well, by reducing the how much it's submerged, you're going to make it more efficient, something along those lines. The alternative is people who provided additional information. So people who talked about Bernoulli or Venturi, people who said that because the water is traveling faster over the top of the hydrofoil, that's what causes the low pressure. That was something that was enough for me to give you the 3rd mark. Okay, so we're going to move on. Okay, why do aircraft typically have a lower factor of safety? Well, so elevators have a factor of safety of 11, and there would be no modern aeroplane that has a factor of safety as high as 2. So why is it that we can get away with having planes, and why would we want planes to have a lower factor of safety? Don't we want people to be safe? Okay, so the reason why we want to have lighter material, by having a lower factor of safety, we're reducing the weight of the plane, allows us to put more payload, and it makes the plane more efficient, right? Less carbon dioxide per flight. That's the benefit. Then how do we provide this? We don't get anything for nothing. How do we justify this? Well, we justify it by having regular inspections and very extensive maintenance schedules. So that's how we can justify this lower standard, this lower factor of safety. Okay, so the next thing we're going to do is we're going to look at lift, and this is my last calculation. So the first thing I always say is I want you to draw a line down, and then we're going to remember that weight is always down. So it's the definite weight. Down is defined as the direction that things fall. The path that they take is vertical. Right? Vertical is defined as the direction or the path that things take when they fall. Right? This is how we find verticality with plumb bobs and things. Now, and also important to remember that weight is the hypotenuse. It's always going to be the biggest value. So if we know that, straight away we can draw this triangle. We can say that lift is always produced perpendicular to the wing. Lift is always produced perpendicular to the wing, and we have 2 forces acting in line with the wing. We have thrust and drag, right? I use the term TH minus D. I sometimes call that thud, but here I've written it as TH for thrust minus drag. Now, because we know that weight is the hypotenuse, we know that lift is going to be close, right? Maybe 80 to 90%. So if I've told you that it's 800 kilonewtons, well, lift is going to be, I don't know, 750. right? 720, something like that, right? So that by knowing that it's going to be in that range, we can straight away, if you wrote 720, I'd pay it, right? I just, oh, well, I didn't have a ruler, I didn't have a calculator, so I just took 90%. Yeah, that's fine. I'm okay with that. I think 90% is actually a pretty reasonable estimate. We found that it was actually a little bit closer, more than 90%. It was actually 756. And we found that by knowing our trigonometry, we know that it's because it's adjacent to the angle of 19 degrees. We can use ca, and so we say cos theta equals adjacent over hypotenuse. So we can rewrite that formula saying lift equals 800 times cos 19, which gives us our value. And we should know that this the line that is opposite the angle is going to be like a quarter or something like that of the hypotenuse. Okay, so we can move on. That's our last calculation. Okay, we've got three different kinds of modulation. The first one is frequency modulation. We can see that it's getting tighter and wider. So the frequency, the number of times that this wave is moving back and forth, is increasing or decreasing. That's the frequency. The number of waves per second is the frequency. We can see here that there's more waves per second than there is there. It's less, there's fewer, right? That's the frequency is what's changing. Here we have phase modulation. What's happening with phase modulation is the thing is just changing direction. It's literally just turning around, right? And that's phase modulation, which we use in Bluetooth, Wi-Fi, and satellites. And then we have AM, amplitude modulation. What we're modulating is the amplitude or the height of the graph, or the volume of the wave. And I like to use the analogy of, or the mnemonic of Arctic Monkeys have an album called AM, and their hit off that album, which is Do I Want to Know? If you watch that film clip, you can see a lot of images that represent sort of amplitude modulation. Okay, this is an easier question relative. I should point out that the lift is an fairly easy question. It's only worth 2 marks. It's definitely reasonable that if a lot of people didn't get that correct, and what I would suggest is those students should be doing more practice questions on lift. I have a folder of questions in Google Classroom, and I have videos explaining the answers, because often we ask you to find lift to drag ratios or something else like that, which requires a much more extensive understanding than that question assessed. This question here, you're not being asked to draw the modulation, and that's much easier. In the past, in other trials, I've asked you to draw this modulation, and that's much more difficult. Here you just have to be able to identify it. Okay, so lastly, I've got a couple more questions. Describe 2 electrical components that use a semiconductor. So if you just said diode and transistor, I would have given you 1 mark. If you said diodes are used in LEDs and transistors are used as switches, I would have given you 1 mark. If you said 2 marks. If you said diodes restrict the flow of electricity, or diodes are used in voltage regulation, Zener diodes, I would have given you 1 mark for that. And then for transistors, if you said transistors are used in logic gates and are the basis of modern computers, I would have given you a mark for that. So I'm looking for just a short sentence on each of those 2. There are other forms of semiconductors, but I'm not going to go into them because they're not really relevant at the HSC level. Okay, so here we have the 3 different orbits of satellites: low, medium, and geostationary. And what we're going to be looking at here is satellites. Now, I had given you homework specifically talking about this. We've talked about the orbit. So we said Starlink is low, GPS is mid, and satellite TV is geosynchronous. The idea that if you, let's say you want to watch Portuguese TV, you buy a 2.5 meter satellite dish, you set it up outside, you point it into one spot of the sky, right, between the constellation Leo or whatever, and that's where that satellite that's going to be broadcasting your Brazilian telenovas is going to be forever. Here I've gone into some of the differences, and the differences are that the main difference in terms of internet quality, why would anyone want to have low Earth orbit, is not because of the bandwidth, it's because of the latency or the ping. So the idea that if you're playing a first-person shooter, it's really important. Ping is a critical detail, because that's the time that you have to react to the people around you, right? So you don't get headshotted. Whereas if you're watching Netflix, if you've got 10 seconds to buffer that video, which you don't even notice, that happens in the dun-dun part of the Netflix. from there on, you're just watching the whole show. It's just still streaming the same speed of internet. It's just because it doesn't need to change. It can buffer, whereas a first-person shooter can't. Okay, so what are the downsides to low Earth orbit? Why do we have any consideration, or why is this just not the norm? Well, for starters, you need a lot more satellites, right? There's a lot more cost involved. And there's a lot of people arguing that it may not be financially viable to have low Earth satellites compared to the benefit of geostationary, with the exception of very few people. So aside from gamers, the other people are maybe people who are using the computers for very high-tech investments. So people who are crypto mining, or people who have bots that are doing trades, and they're doing several trades per second, they might need that latency. But otherwise, there's very few roles that I can think of that would really need that level of precision. Maybe if you're doing surgery via a satellite, which I don't think is a thing that anyone's ever attempted. Not yet. Are there any other problems? Yes, there's also the problem of deorbiting. So the low Earth orbit satellites are more likely to fall out of orbits. They are more likely to create space junk because there's so many of them. They also have a much bigger impact on astronomy. So scientists all over the world are concerned about the number of satellites that are polluting the night sky, making it harder for us to understand what's going on in other galaxies. Okay, so for modulation, I've already passed this, but we'll just quickly talk about. We've got some comments about AM, FM modulation. Yeah, not really too concerned about that, but we can see here, this is an example of being able to recognize what kind of modulation. So that's phase, and yeah, again, we can see what kind of modulation is this one. What's changing? The frequency. Okay. But I think when I gave you this task, I actually had like a homework sheet, or when we did the essentials, I gave you a homework sheet where I asked you to draw them. Okay, so moving on. Okay, so we've done the internet. Okay, last question is copper. So we'll go back to, I now have a sheet on copper. So we have ETP, so electrolytic tough pitch, is 99 is the standard. That's what we use as 100, the 100% standard for conductivity. It's 99.9% pure copper. The silver isn't counted as an impurity. Why? Because silver is more conductive than copper. OFHC is even better. It's 99.99% pure. I would reference LEG if this wasn't the third time I'm recording this video. And what we've got is the three other main ones we're interested in is copper beryllium, or cube. I like to think that the Rubik's cube is hard, so it can be precipitation hardened, copper beryllium, and it can be used in tools. So the reason why we use it for tools is because it doesn't spark. Now, I don't know why it doesn't spark. Maybe the conductivity, maybe it needs to be beryllium so it can be hard enough to be suitable for tools. You couldn't use just regular copper for tools, I'm guessing. But yeah, if you're working on an oil rig, the sparking is a real thing. They're very expensive. We also have copper cadmium. Copper cadmium has, it's suited for large diameter applications. Why? Because it has good thermal properties, and it's useful for things like overhead wiring in trains and trams. And then finally, we have brasses. If you see copper zinc in an exam, you might. Copper zinc is another way that we can refer to brass, and it has good corrosion resistance. So that's a short summary of the different things. I didn't ask you about copper brass, but that's what we're going with here. So describe the properties of one of these specialties. So if you said copper beryllium, it is not as conductive as ATP, but it can be much harder and is suitable in areas where sparking may be a problem. I gave you a little bit extra there. You probably didn't. You only needed to say in areas where hardness is a problem, where wear resistance is needed. That would have been fine. Same thing with copper cadmium. We can say copper cadmium is suitable where heat is a problem, typically things with large diameters, such as overhead wiring. That would be a very extensive answer for 2 marks. Okay. That is it for the 2022 trial.